My dear student, colleagues, and all the viewers who are watching this program live from Facebook page and YouTube channel, I would like to welcome you all to our International Physics webinar. Today it's our 105th International Physics webinar. Good evening to all here in Bangladesh and a very good afternoon to all those who are watching this program live from UK. Happy Victory Month, and we celebrate our Victory Day yesterday with a Nobel laureate, and today it's our 105th International Physics webinar. Hope you are well and safe from Corona pandemic, and all we know that we are staying in a Corona pandemic situation. We cannot continue our normal academic program inside the campus, so we have to start our online program to continue our academic program. Our Department of Physics, Pabna University of Science and Technology, has started this online program. We have also started online international physics webinar. We have successfully completed our 104th international physics webinar. Today it's our 105th, and we are trying to adjust with this new normal situation. So today is very important day for our department. Today I'd like to welcome you all to a joint session between the Department of Physics and the Gravitational Astrophysics and Cosmology, University of Glasgow, UK in Physics. And we have with us here today Dr. Martin Hendry, sir, Professor Gravitational Astrophysics and Cosmology, University of Glasgow, UK, connecting us from UK, and he has already connected with us. So I'd like to welcome our speakers. So sir, good evening and good afternoon to your parts. Welcome to our International Physics webinar, and welcome to our university and Bangladesh through online. So we'd like to say thanks on the behalf of the Department of Physics, Pabna University of Science and Technology, for accepting our invitation, sir. So for those who are new, I'd like to inform that we have divided our webinar into three parts. First of all, we'd like to introduce our speaker with all of you, and then our speaker will deliver his speech, and at the end we have a discussion time. In that time, anybody can join with us. So the main aim of our program is to motivate and encourage our students in this Corona pandemic situation. We are trying our best to do that. So I think you have already come to know the title of this today's International Physics webinar, and title is the Exploring the Dark Side of the Universe. And our speaker is the Dr. Martin Hendry, sir, Professor Gravitational Astrophysics and Cosmology, University of Glasgow, UK. And we can see his educational and professional background. He's a professor of Gravitational Astrophysics and Cosmology in the School of Physics and Astronomy at the University of Glasgow, where he was first appointed as a faculty member in 1998. He's a member of the Institute of Gravitational Research and the Astronomy and Astrophysics Research Group, where he was a PDRA working in cosmology from 1996 to 1998, and where he also completed his PhD in 1992. He is a passionate enthusiast for public engagement in science and was a Science in Society Fellow for the Science and Technology Facilities Council, leading an international program of outreach with schools and the public entitled Exploring the Dark.
Hello. Firstly, I'm checking if you can hear me because I lost the connection. I couldn't hear the end of Pretam's introduction. So I wonder if you can verify that I am still connected. Okay, so I'm trying to check if my slides can be seen. I don't want to begin the presentation until we're sure of that.
Sorry, sir. Sorry, the viewers and students. We have a internet problem. So
No problem.
we have again. Okay, so we. So he's a fellow of the Institute of Physics from 2015 to 2017. He was a chair of the Institute of Physics in Scotland, and he currently chaired the IOP Scotland Education Committee. He is also co-organizer Glasgow's monthly Cafe Scientific at the Tron Theatre. In 2011, he was elected as fellow of the Royal Society of Edinburgh in recognition of his contribution to research, teaching, and the public understanding of science. In January 2015, he was awarded an MBE for services to public engagement in science in the Queen's New Year Honours list. In 2015, he was also awarded the Society of Edinburgh Senior Prize for Public Engagement. Research interest. His principal research interests lie in gravitational wave astronomy, particularly the use of future gravitational wave observation to constrain the cosmological parameters and issues relating to the optimal combination of data from gravitational wave source and their electromagnetic counterpart. Two, the statistical methods for the analysis of cosmological data sets, particularly large-scale glasses, redshift, and particularly peculiar velocity surveys and the survey of the high redshift supernova. Three, application of the gravitational lensing, including diagnosis of the planetary and stellar atmospheres, circumstellar envelopes, and stellar winds, and the lensing as probe of the nature and distribution of dark matter. We can see his publication, and this is his Google Scholar ID. We can see his citation number is 44,688. So thanks for all of your patience, and I'm sorry for internet problem. So I would like to welcome our speaker again. So thanks again, sir, for accepting our invitation. It's your time. You can start your session, sir.
Thank you very much, and I hope that the connection will be good for us throughout my presentation. I'm delighted to be joining you again. I think this is a tremendous opportunity to share some exciting recent discoveries, but in this talk I'm also going to survey more of the history of our subject. Now, I just want to check that everyone can hear me. I am hearing a slight echo. I'm hoping that won't be a problem. So I'm going to reduce my volume to avoid that echo becoming too bad. And we'll get started in just a moment. Right. Okay. So I've called this talk Exploring the Dark Side of the Universe. And maybe some of you remember that I gave another lecture just a few weeks ago, back in October. And that was focused on gravitational astrophysics and the observation of gravitational waves. So it's been a very exciting time for gravitational wave astronomy in the last few years because of the discovery of the very first collisions of binary black hole mergers just over 5 years ago. And that led to the award of the Nobel Prize for Physics in 2017 to 3 of my colleagues in the LIGO scientific collaboration. But today, I'm going to focus much more on cosmology. And my research over my career has focused on many big questions about cosmology. How big is the universe? How did it begin? Why is it expanding? And it's a real honor to be talking about this to you today, because I understand you recently had a lecture by James Peebles, who was awarded the Nobel Prize in Physics in 2019, 2 years after my LIGO colleagues. So I am not going to repeat, to replicate the themes of Jim Peebles' research, but I'm going to try to develop some themes which are complementary to perhaps the topics that he has discussed. He was awarded the Nobel Prize for theoretical discoveries in physical cosmology, essentially building a theoretical picture which allowed us to understand the origins of our universe. Not completely, there are still many unanswered questions, but in general terms, the picture of a hot Big Bang and an expanding universe. So I'm going to build on that and to focus on some specific aspects of that model, the hot Big Bang theory, and to look at how current observations are challenging aspects of that theory, and indeed how current observations are perhaps suggesting that there are still some unanswered questions, some significant unanswered questions around the nature of the dark side of the universe. So hence the title of my talk. So the outline is that I'm going to begin by briefly surveying a century of cosmological observations, the evidence we have for the Big Bang and for the existence of dark matter and dark energy. And I will do that mainly just using diagrams and pictures and not any equations. But I will then have a brief section where I look at some of the underpinning equations of cosmology, what we call the Friedmann equation and the cosmological models that we can understand in terms of the Friedmann equation. And then next, I will look specifically at the cosmic microwave background radiation. Now, perhaps that was discussed by Professor Peebles, but I'll return to it a little more to look at how useful it has become as a way of probing cosmological models. But what the last few years have revealed is an interesting tension, an interesting complication, which is when we attempt to estimate the current expansion rate of the universe using methods which are more traditional, essentially building on the original work of Edwin Hubble himself. And when we compare those methods with estimating the expansion rate from the cosmic background radiation. And this tension, this disagreement in the measurements of that expansion rate is presenting some real puzzles for our understanding of our universe. So I will look at what those puzzles are and some possible ways in which we might resolve them in the relatively near future. So that's the plan for my lecture. And I'm going to begin around the time when I was doing my PhD. In 1990, I had just begun my PhD 1 year before, and that's when the Hubble Space Telescope was launched. And it has been a crucial astronomical observatory for many aspects of cosmology. One of the things that the Hubble telescope did in 1995, and then several times more in the years that followed, is it took a very deep image of the distant universe. We call this the Hubble Deep Field. So the idea was to find an area of the sky where there are not many bright stars, and to observe it for a long time, a long exposure image, to reveal the very faint details of distant galaxies that would be drowned out in a region of the sky with too many bright stars. So this first Hubble Deep Field was in a region of the sky close to the familiar constellation of Orion the Hunter, and we'll just see what that deep field image revealed. So as the image reveals itself, what we see are galaxies which are so distant that the light has been traveling towards us for many billions of years. And how do we know this? Well, if we take the galaxy images in that Hubble Deep Field, and for example, we combine those observations with measurements of the spectrum of light from those distant galaxies, including some which are almost invisible. You can see this very faint smudge of light here in red, circled by the red circle. And that was studied by these telescopes here, the Very Large Telescope Array in Chile, splitting the colors of light across the electromagnetic spectrum, dispersing that light so that spectral lines could be identified. And that allowed us to determine what we call the redshift of that galaxy. And that redshift revealed that this galaxy that we see as this tiny smudge of red is so distant that the light has been traveling for perhaps 12 or even 13 billion years. So we really are looking at galaxies a long time ago, which are far, far away. Now, that gives us this dramatic picture of our evolving universe. So as the Hubble telescope looks back to those most distant objects, it's seeing a universe that was much younger, but also much denser and hotter. Because we've learned over the last 100 years, culminating in the observations of, for example, the Hubble Deep Field, that our universe is expanding. And that points towards a theory for the origin of the universe, which says that that expansion began with what we call the hot Big Bang. So the expanding universe is going to be the first major theme of my talk this afternoon. And I'm going to begin by focusing on the early 20th century, so about 100 years ago, when at that time we did not yet know that there was a whole universe beyond the Milky Way galaxy, our own galaxy. There was a key question that was unresolved among astronomers at that time, and it concerned objects like are shown here, which were called spiral nebulae. Now, nowadays, we know that these are galaxies. In fact, they're rather similar to our own Milky Way galaxy. But 100 years ago, that was not yet appreciated. And a key question was whether these spiral nebulae were relatively small gas clouds within the Milky Way or completely outside of the Milky Way, what some astronomers rather poetically called island universes. Now, to answer this question, are the nebulae in the Milky Way or beyond the Milky Way, what we needed to do was to measure their distance. And Edwin Hubble was one of the first astronomers to do exactly this. He was building on the work of other astronomers, including Henrietta Leavitt from the early 1900s, that established the existence of particular types of star, which are very good distance indicators. We call these stars Cepheid variables. They vary in brightness, and we understand that they are varying in brightness because they are pulsating. And the cartoon you are seeing is illustrating that in this model of a pulsating Cepheid, then the brighter the Cepheid, the larger the star becomes, but the longer it takes the Cepheid to complete one cycle of its pulsation. So if we can measure how long it takes a particular Cepheid to pulsate, we can estimate its intrinsic size and luminosity. And then we compare that with how bright the Cepheid appears to be, and that gives us an indication of the Cepheid's distance. So we call this procedure using stars as standard candles, because basically we're using the pulsation period of the Cepheid to indicate how luminous the candle, the star, is. And if we know how luminous stars are, we can estimate their distance from their apparent brightness. So Edwin Hubble was able to observe these Cepheid variables in the spiral nebula known as the Andromeda Nebula. And that straight away revealed that these Cepheids were beyond our Milky Way galaxy altogether. that what we were learning was that these Cepheids were so distant that in fact the Andromeda Nebula was a separate galaxy, an island universe beyond the Milky Way. So, if these pulsating Cepheids could be used to measure distance, the other aspect of Edwin Hubble's work was to use the spectrum of light from the whole galaxy to measure its redshift. He was looking for spectral lines and noting that compared with the wavelength of those lines in a laboratory spectrum, in distant galaxies, they tended to be shifted towards redder colours or longer wavelengths, hence the name redshift. And Hubble made a diagram plotting the distance inferred from his observations of things like Cepheids versus the velocity inferred from the shifting of the spectral lines, essentially using what we call the Doppler shift that relates the recessional speed of an object that is red shifted in that manner. And this revealed a straight line relationship. And this we now refer to as the Hubblelumetra expansion. This is building upon Hubble's work and the theoretical work of another cosmologist, Georges Lemaitre. This key observation set in motion our modern study of cosmology because it was interpreted as meaning that our universe is expanding. The reason that more distant objects appear to be moving faster away from us is not because they are traveling through space, but because space itself is expanding. This dramatic conclusion from Hubble's observations was consistent with Albert Einstein's general theory of relativity. Albert Einstein's equations almost demanded that the universe ought to be expanding. We will return to that idea in just a few minutes. So here's a cleaned up version of Hubble's diagram. We can see quite clearly that straight line relation, but the slope of the relationship, which measures the current expansion rate of the universe, actually Hubble didn't measure that very well at all. And this was due to a combination of factors. His distance indicators were actually not so reliable, and also the velocities that he measured from the redshifts were not purely due to the expansion of the universe. Let's explain what I mean by that. Well, let's understand it in the context of what developed in the decades that followed. Hubble's initial measurement of the expansion rate, well, let's go back to the previous diagram for just one moment. If we measure the slope of that straight line as the difference in the y coordinates divided by the difference in the x coordinates, so that's velocity divided by distance, then you can perhaps see just by eyeball that it's about a range of 1000 in y and a range of about 2 megaparsecs in x. So that gives us about 500 kilometers per second per megaparsec. And that's what we see as the value that Hubble obtained up here. And then there's Lemaitra's value even earlier, but from theoretical considerations. But over the course of the 20th century, as more and more improvements were achieved in the observations, then the measured slope of that relation got smaller and smaller. So by the time I was studying in the 1980s, which is not shown on this graph, but the range of values was down round about 100 kilometers per second per megaparsec. So the key message here is that determining the expansion rate of the universe is actually rather difficult. And we need good distance estimates, but we also need to be measuring the actual velocity due to the expansion of the universe, what we call the recession velocity. The trouble is that for many nearby galaxies, the velocity that we measure is also including another contribution, which is called the peculiar velocity. It's the velocity of the galaxy through space due to the gravitational attraction of its neighbours. And this effect, this distorting peculiar velocity, is particularly strong in a cluster of galaxies. So there's a nearby cluster of galaxies in our cosmic backyard called the Virgo cluster. And we can see that if we plot recession velocity against distance, we don't really get that nice straight line. We get a distortion due to the additional motions of the galaxies in that cluster, not due to the expansion, but due to their own gravitational attraction to each other. So to measure the Hubble constant reliably by these kinds of methods, we want to use nearby galaxies to give more precise distances, but we also want to use distant galaxies to reduce the impact of those peculiar velocities, because the further away a galaxy is, then the smaller this peculiar velocity is as a percentage of the other term due to Hubble's expansion, Hubble and Lemetra's law, which says velocity is proportional to distance, at least nearby. So that's a big challenge. It means that simultaneously we want to use nearby galaxies and distant ones. Well, how do we do that? The answer is to get our estimate of the Hubble constant from combining distances over a range of scales, both nearby and distant. And this involves combining what we call primary distance indicators and secondary distance indicators. It involves doing something that I describe to my students as climbing the cosmic distance ladder. So nearby to us, within just a few megaparsecs, we have reliable distance methods like Cepheids that we talked about before and various others. And then much more distant galaxies, we have reliable methods that are good at getting the relative distance between galaxies. We can tell that this galaxy is twice as distant as that one, but we don't get an absolute distance in megaparsecs. We need to combine with the nearby methods like Cepheids in this distance ladder. So we need secondary indicators to go far enough out that those peculiar velocities are not so important, but we need the primary indicators to link to those secondary indicators. So this was one of the main reasons why the Hubble Space Telescope was launched. It was to resolve the disagreements in the Hubble constant that still existed through the 1980s, largely because of disagreement of how best to climb this cosmic distance ladder. And one of the big problems was that the Cepheids didn't quite go far enough to really effectively link to the distant rungs of the ladder. So the Hubble Space Telescope was designed to solve that problem. One of its many projects was to look for Cepheids in distant spiral galaxies where one could get beyond the regime where those peculiar velocities were a problem. So that effectively meant we could bypass one of the levels on our distance ladder. But it involved finding Cepheids in remote galaxies, like this one. The Cepheid isn't very bright, it's just a few pixels in an image, but you can see that it's varying in brightness. So this basic idea of determining its luminosity from the period of varying in brightness and then getting its distance from using its apparent brightness, that was now being applied at much greater distances than before. And then linking to the secondary distance indicators, that involved a new type of distance indicator like this one. This is a cartoon showing a type 1a supernova that's believed to be a pair of stars, a white dwarf star and a red giant. And the gravity of the white dwarf star is quite intense. It's a very dense star, about the mass of the sun, but only about the size of the Earth. And that's capable of drawing gas from the red giant. So gas flows onto the white dwarf and pushes the white dwarf to a mass beyond which it can remain stable. So the white dwarf explodes, and that gives off a lot of light, a lot of radiation. But what makes these type 1a supernovae so useful is that the brightness of those type 1a supernovae, when the white dwarf becomes unstable and blows up, is pretty similar from one supernova to the next. So this is another example of a standard candle, just like the Cepheids, but this time observable to much greater distances. So in essence, we can use Cepheids within our galaxy and then with the Hubble Space Telescope beyond our galaxy, but not too far into the universe. But we could observe Cepheids far enough that there were examples of type 1a supernovae within those relatively nearby galaxies that could then be linked to much more distant supernovae to give us the Hubble constant. And other methods like the supernovae could be used as well. And this series of diagrams shows the final results from that Hubble telescope key project. And essentially, what that did was to narrow down the uncertainty in the Hubble constant, the expansion rate of the universe, to about 10%, which compared with Hubble's original measurement, and even when I was a student in the 1980s and 90s, that was a huge improvement. But we still wanted to do better, and we'll come back to that theme a little later. But just reflect on how much that data had improved. This circle here shows the range of Hubble's original data. And remember, there were those problems with peculiar velocities contaminating his results. But with the Hubble Key Project, we were going many tens of times further and deeper into the universe. Now, that's all about measuring the current expansion rate of the universe. But at the same time, astronomers were thinking about this question: is the cosmic expansion slowing down? Because the basic framework of Albert Einstein's theory of general relativity tells us that the universe ought to be slowing down because of the gravitational attraction of all the matter in the universe trying to pull it back together. So a key question was whether, perhaps, the universe might reach a maximum size and then begin to collapse again. If there was enough matter in the universe, then that scenario was entirely possible. So astronomers through the 1970s and 1980s were trying to answer that question as well. So they were looking even deeper into the universe to try to see evidence of how the expansion rate was changing, but they were also trying to measure how much matter there was in the universe to see if theoretically it ought to be the case that the universe was slowing down enough to eventually stop and begin to collapse again. So a lot of that work involved studying individual galaxies, work by people like Vera Rubin, studying the rotation of galaxies, and using that information to work out how much mass was contained within and around the galaxy. And what Vera Rubin found was that galaxies were spinning faster than they should be if the only gravitating mass was the luminous material that we see in an image like this one. So what that gave some impetus to was the development of the idea of dark matter. The concept that a galaxy like ours has luminous material in the form of stars and gas, but it's embedded in a roughly spherical halo of dark matter, which contains perhaps about 10 times as much matter as the luminous stars and gas. So what exactly is this dark matter? Are we even sure that it exists? Well, over the last 30 years, we've been able to infer the existence of dark matter in other ways as well. What you see here is a computer simulation about how galaxies and clusters might form. And the colours here are not denoting light. What they're denoting is how much matter there is. And in this computer simulation, most of the matter is dark. It's not in the form of stars and gas. It's in the form of matter which has a gravitational pull, but otherwise doesn't really do anything at all. And in fact, we call this cold dark matter because the matter isn't moving close to the speed of light. If it were, we would call it hot dark matter. So it's just kind of sitting there in the universe, doing not very much, but influencing how the luminous material clusters together and moves around. So what is this cold dark matter made of? Well, at the same time as all of that was going on, we were developing increasingly sophisticated understanding of the very early universe. I don't have too much time to talk about this. There's so much to cover. But let me just say that what we developed was a way to predict the abundances of different chemical elements. The very lightest chemical elements, we believe, were manufactured during the first few minutes after the universe began. When this Big Bang happened, it was incredibly hot, it expanded and cooled, and has continued to expand ever since. But during those first 3 minutes is when, for example, most of the hydrogen and helium, and even much of the lithium and beryllium was made. So our understanding of that very early period after the Big Bang allows us to predict the abundances of these chemical elements, but the theory only works if most of the dark matter is not made of atoms. So the dark matter that we deduce from observations of galaxies and the rotation speed of galaxies, the dark matter that we deduce from our computer simulations of how galaxies might form, all of that seems to argue that the dark matter is made of something else that isn't atoms. We call this non-baryonic dark matter. It's not made of protons or neutrons. And therefore, what is it made of? We don't know. We would like to know, of course, and there are many different ways to try to answer that question. Some of them using astronomical observations, some of them using particle physics experiments. We have some candidates for what the dark matter might be, but we still don't know what the dark matter is. That's one of the biggest unanswered questions in all of astronomy. And as if that weren't enough, the realization that there's a lot of dark matter in the universe was in the context, remember, of trying to answer the question, is the cosmic expansion slowing down? Astronomers thought it was, but they were unsure if it was slowing down enough to ever recollapse again. But then using those type 1a supernovae that we talked about before, but using them even more remotely, further and deeper into the universe and further and deeper into the past, what it was possible to do was to realize that the universe is changing in its expansion, as expected, but in fact, it's speeding up instead of slowing down. We think that it was initially slowing down for several billion years, but a few billion years ago, it began to speed up. And that's weird. And we give, as an explanation for this phenomenon, a name which, well, it sounds rather cool as a name. We call it dark energy. But we don't know truly what the nature of dark energy is. It's another big unanswered question about our universe. Now, the observation that the universe is speeding up argues for some kind of mechanism to be driving that. That's what we call dark energy. And that's a very open question, exactly what dark energy is and precisely how it drives this speeding up, this accelerated expansion. But the fact that the universe is speeding up is much less controversial. That is generally accepted now. And in fact, it was awarded the Nobel Prize in 2011 to these three astronomers here. But explaining why the universe is speeding up is a very different matter. So essentially, our current state of the universe poses this huge pair of questions. Why should it be that the ordinary matter made of atoms like us constitutes only about 5% of our universe? And why does the remaining 95% seem to consist of strange matter and energy, the nature of which is a big mystery? So what I'm going to do next is, having surveyed the universe very quickly, I'm going to just flesh out a little bit some of the underpinning theory. There won't be time to do very much of this, but I do want to share some of it with you to give some insight into how we conduct research to model the universe. So the key principle that we use is the idea that the universe on its very largest scales is homogeneous and isotropic. There's good evidence from this from, for example, galaxy surveys, where we make maps of galaxies in the universe. And what I mean by that is that the structure that's apparent on small scales, well, if we look at bigger and bigger scales, imagine drawing larger and larger circles in this diagram, then the structure starts to look pretty similar. Okay, it's not so similar at the edge, but that's because our telescopes aren't good enough to see the galaxies at those great distances. We think they're there, but we need better telescopes to observe them. And then there's this cosmic microwave background radiation that I mentioned before, which looks very isotropic. It looks uniform in all directions. We'll come back to the CMBR in a few minutes. So using Einstein's theory of general relativity, we can construct models for that homogeneous and isotropic universe that the cosmological principle supposes exists. And we can describe the universe in terms of a scale factor, which is dependent on time, the time since the Big Bang, and is a measure of how much the universe has expanded. And that expansion we observe a consequence of it as redshifting the radiation from distant galaxies and distant stars, distant supernovae. And the geometry of the universe, which is this described by this constant k in the metric of our isotropic and homogeneous universe, we could think of that geometry in a two-dimensional analogy as being either closed or open or flat, like these three surfaces seen here. And therefore, we don't know a priori which geometry our universe has, but we might hope to measure it by making observations of the distant universe. And we do that by fitting our observations to particular equations. So equations about the expansion rate of the universe, that's called the first Friedmann equation. And then there's a second equation about the acceleration of the scale factor. And the terms that appear here are things like the density and the pressure of the universe, the scale factor that we talked about before. And then there's also this term called lambda, which is introduced as a kind of integration constant into the equations. But in fact, Einstein initially wanted lambda to have a value to make the universe static, because when he first formulated his theory, no one knew that the universe was expanding. But then along comes Hubble and the theory of Hubblelumetra, and that suggested that actually it was quite natural for the universe to be expanding, and that suggested that maybe this lambda term wasn't needed in the form that Einstein supposed, but the term could still be non-zero anyway. And in fact, that seems to be the type of universe that we live in. So Einstein had the last laugh in terms of his so-called cosmological constant, because that's essentially what we think dark energy might be. So here's a diagram that shows the solutions to this equation, this Friedmann equation for the expansion rate squared, in terms of a series of graphs. And we can see that we can have universes that expand forever, or we can have universes that collapse, and that will depend on the values of the different terms in this equation. So basically, the job of cosmology is to make measurements that will constrain or measure for us the values of those terms, and then basically tell us which of these curves describes our real universe. So we can measure the present day slope, as we talked about before. That's like the region close to the present day, going backwards in time. And in fact, in the relatively near future, we also would not see a change in that slope. But if we go far enough into the past or far enough into the future, then the curves diverge depending on the values of these different terms in the Friedmann equation. Now, often it's convenient to write the Friedmann equation in dimensionless form. So what we have is these three quantities, omega, omega mater, omega lambda, and omega k, to do with the curvature k. And in fact, we arrange that they add up to 1. So our task is to measure these omega parameters. So what values do they have? Well, just before we get to that, I'm not going to talk much about this slide. It's just to emphasize that we can model how those omega parameters will change over cosmic time. That's basically how we solve to get these different curves in a diagram like this one. So there's particular equations that determine all of that. And the point is that the expansion rate will be dominated by different terms at different redshifts. So it might be that in the early universe, omega mater is the most important. Remember, that was this one here. Whereas later, omega lambda might become much more important. So we have some interesting questions to think about, not just about measuring the values of these parameters now, but how they evolve in the future and how they evolved in the past to reach the current day situation. So remember, we said that with some simplifying assumptions, we can arrange for these three omegas to add up to 1. Well, in fact, our observations strongly suggest that omega k is very close to 0. And it's very commonly the case that we argue that omega k is in fact exactly 0. Because if omega k was different from 0 in the past, then it's very hard to understand why it's still so close to 0 now. Or another way we can think about that is, if we look at the other two parameters added together and just call that omega, then the sum of those two will be very close to 1 if omega k is very close to 0. But the value of that sum will change a lot as the universe evolves. So they would have needed to be incredibly close to 1 just a few seconds after the Big Bang to still be so close to 1 today. So again, just to put that in the context of the earlier equations, what I'm saying is that what was called omega in the previous slide and in this slide is the sum of these two. And if omega k is not 0, but just close to 0, then we can see that after 1 second, we need to be incredibly close to 1 for the sum of these two, in order that at the present day, we are still within even a factor of 2 of omega mater plus omega lambda equals 1. So all of this sets some theoretical context for what is called inflation, a theory that says in the very early universe, our patch of the observable universe expanded very quickly. And what that did was it meant that the universe that we observe today is really just a small patch of that initial universe. And that means we can use a helpful analogy to think of a small patch of the surface of the Earth. We know that the Earth is curved, but a small patch of the Earth looks flat. So that's why our universe looks as if it has k equals 0. It doesn't mean that the entire universe necessarily has k equals 0, because that inflationary expansion will drive the universe towards k equals 0. So did inflation happen? Well, that's another one of the big unanswered questions in cosmology. It's a very popular theory because it explains many things, not just this issue about the flatness of the universe, but it also explains or provides one explanation for the temperature variations in the cosmic background radiation. Some slides ago, I showed that as a red oval, indicating that it was almost the same temperature in all directions. But it's not exactly the same temperature in all directions. And the variations in temperature, according to inflation, were amplified from quantum fluctuations in a tiny fraction of a second after the Big Bang to now be observable by us today in this cosmic background radiation. So let me say a few words about that. I don't have very much more to go, but I do want to say a little bit about the CMBR, the Cosmic Microwave Background. So Jim Peebles, our wonderful Nobel laureate from 2019, was involved in the very early days of this. So one of the reasons he was awarded the Nobel Prize was because of his enormous contributions to our understanding of this field. The idea is that the cosmic microwave background is relic radiation from the Big Bang itself, which has been cooling as the universe expanded. And Jim Peebles and others predicted that such radiation should exist and should have a black body form that was emitted when the universe was much younger and hotter. It should have been emitted when the universe was about 3000 Kelvin, much hotter than it is now. And it came from a time when the universe was transitioning from being fully ionized to being electrically neutral. So before that time, the universe was so hot that neutral hydrogen and other atoms couldn't exist. That meant there were lots of free electrons around, and electrons are very good at scattering light, like in a fog. But after about 380,000 years, the universe had cooled down enough that those protons, the nuclei of hydrogen atoms, and electrons could recombine, or combine really, because they'd never been combined before. But we call it the epoch of recombination. And that means that light can now stream freely because free electrons are very good at scattering light, but neutral hydrogen, not so good. So this is a bit like a fog clearing. And we say that the CMBR is like the edge of a fog bank, the surface of last scattering, beyond which light cannot penetrate because it's scattered too much by the cosmic background, the ionized hydrogen that existed back then. So this CMBR was first discovered in 1965, and it was then characterized much more precisely in 1989 by a satellite called the Cosmic Background Explorer. And what it revealed was that the radiation is indeed a black body, and it has an incredibly precise black body temperature of 2.725 degrees Kelvin. And then, a few years later, COBE detected some tiny variations in temperature, but only at the level of a few hundred thousandths of a degree. But remember, these variations are just what we expect because they're believed to be the seeds of the clustering of galaxies that we see around us today, and they're put there, they're the relics of the quantum fluctuations that existed in the very early universe. At least that's what inflation says they are. Now, more recently, in the last 20 years, we've been able to map those temperature fluctuations much more precisely with the Wilkinson Microwave Anisotropy Probe, or WMAP, and also Planck, another satellite, but in addition, a number of experiments on the surface of the Earth looking at particular frequency ranges of the CMBR. And altogether, what that's done is revealed the precise details of the temperature variations. And that's given us maps like this one, with that incredible detail shown as different colors representing different temperatures. And what that's allowed us to do is to make maps of how the temperature varies and relate that to the theory of how much variation one might expect. So we do this by making what's called the angular power spectrum of the cosmic background radiation. And roughly speaking, it involves averaging the temperature over patches of the sky of different size. So big patches get averaged and give us the power spectrum on small angular scale, on small multiples. And then small patches, small angular scales, they give us the power spectrum corresponding to large multiples. So these multiples are a way of describing the cosmic background radiation in a mathematically compact way, using functions called spherical harmonics that describe these variations on temperature on different angular scales. And this is the kind of results that have been obtained. This is from the Planck satellite. It shows this power spectrum on different angular scales. So the small scales are up here, the larger scales are down here. And what we can do is we can compare these observations with theoretical predictions. Again, linking it all back to the Friedmann equation we saw before, and seeing what that tells us about the values of the different terms in the Friedmann equation, and also the Hubble constant. But the Hubble constant's a little tricky to get from these data because it appears in several different places. It's what we call degenerate with the other parameters. But what we can do is we can combine that kind of data with observations of supernovae, like what we talked about before, and various other measurements. Remember, the measurement of the Hubble constant more directly from the nearby universe, that was the Hubble Telescope Key Project. And there's another very useful method called baryon acoustic oscillations, which is looking at the clustering properties of galaxies in the not quite so distant universe. Putting all of that together allows us to try to constrain the parameters in the Friedmann equation. And here's a slide that I showed in a talk more than 10 years ago, where already we were beginning to do that really quite well. So what you see here is the omega matter and omega lambda that appeared in the Friedmann equations in its dimensionless form. And by combining different data sets, we were basically saying that the universe was very close to flat. Look at how the best fit overlap really lies on the line that corresponds to a flat universe. But the presence of the lambda term was strongly supported by the supernova observations, although the precise measurement of omega lambda really only gets good when you combine the supernovae with other things, like baryon acoustic oscillations or the cosmic background radiation. Now, we could also parameterize the expansion of the universe in a slightly different way. We could look at something called the equation of state that relates the density of the universe to its pressure. And essentially, a lambda, a cosmological constant, would correspond to a W of -1. So in fact, if we fit those parameters, then yes, back in 2009, we were already finding that the combination of all these different methods was giving a value of W close to -1. But was it exactly -1? We would like to know that, of course, because that would tell us whether the universe is described by truly this cosmological constant, a constant dark energy term, or something more exotic. So there's been many developments in the decades since. Here's a much more recent observation of distant supernova from what's called the Dark Energy Survey, and we can see that it's still agreeing very much with a speeding up universe, and it seems to agree with an omega matter of about 0.3 and an omega lambda of about 0.7, or a W very close to -1. Or another way we can look at it, similar to the previous slide, this is now from last year, is again showing how tightly we seem to be fitting a flat universe. Or if we look at W, again, we're constraining W to be around -1, but we would like to be able to probe the precise nature of this W rather more deeply. And that brings me to the final brief topic. because underpinning all of that and the huge improvement there's been in our ability to measure this dark sector, the dark matter and the dark energy, and maybe even begin to ask questions about the nature of the dark energy, at the same time, something very puzzling has been going on with the Hubble constant. Because there's a split now between measurements of the Hubble constant using things like supernovae and Cepheids that we talked about before, and using the microwave background radiation and, if you like, reverse engineering from the CMBR to the present expansion rate. Those two methods are not giving good agreement. And in fact, recent studies of this by people like Adam Rees, one of the Nobel Prize winners from 2011, are showing a really strong disagreement between the late methods, the nearby observations of things like supernovae, and the early methods like observing the CMBR. They're quite strongly disagreement. So what does this mean? Well, what do we make of this? I'm borrowing this slide from Rocky Kolb, a very eminent cosmologist that was talking about this a couple of years ago. There's a possible set of explanations that just involve a lack of understanding, or maybe even some problems with our measurements. Or there's a real problem with our theory, meaning that this idea of a cosmological constant in the form of dark energy is maybe just not quite right. Maybe that lambda is not a complete enough model. Maybe we need to describe the expansion rate of our universe not with lambda and cold dark matter, the so-called lambda CDM or concordance model, but something else. So I mentioned a little earlier that we can look at the evolution of the expansion rate in terms of different components. And the lambda term is a kind of vacuum energy density, which according to the simplest model is constant everywhere. But maybe that vacuum energy density actually varies in time, which means it would vary in redshift. And one of the reasons why that would be appealing is that otherwise we've got another puzzle to explain, which is why the values of omega lambda, if lambda really is constant, and omega matter are rather similar to each other today. Because in the distant past, omega matter was completely dominant, and in the not too distant future, omega lambda will be completely dominant. So it seems to indicate that we live at a rather special time. And why should that be? Might it not be more natural that omega matter and omega lambda are not the full story, and the actual evolution of these parameters kind of tracks each other in a way that means there's nothing special about our current time? So that would involve some kind of W parameter that actually depends on Z. And one way of calling that is to describe it as a generalized dark energy or quintessence model. Now, there's a ton of different theory that can be developed around that, but we can also try to measure W as a function of redshift. And we can do that using the electromagnetic spectrum. So there are plans to do that in the future using a range of different telescopes and missions. But we can also do it using gravitational waves. So just to briefly return in the final 2 minutes to the topic I covered in my first lecture a few weeks ago, we might hope to constrain the properties of dark energy, this W as a function of redshift, using not standard candles, but standard sirens, using gravitational wave sources as a way of probing the distant universe. I'm sure we'll continue to use standard candles as well, but maybe gravitational waves could have an additional role to complement the electromagnetic measurements. Now, we will need to wait before we can do this. The current generation of gravitational wave detectors, which I talked about in my previous lecture, will not probe deep enough to really do this. But the next generation in the 2030s should be capable. Instruments like the so-called Einstein telescope or Cosmic Explorer, which are under development in the Europe and US communities would have the capability, we think, to probe deep enough into the universe to try to measure this W parameter, the properties of dark energy as a function of cosmic time. And what this plot shows, I know I'm rushing a little, but I just want to emphasize that as we try to model that W of Z, we can forecast how well gravitational wave observations in the future might do this. And the crucial thing to note is that they can do approximately as well as electromagnetic observations using things like the CMBR or baryon acoustic oscillations or supernovae. So gravitational wave standard sirens will be competitive for the cosmology of the 2030s. And indeed, the LISA spaceborne detector that will launch in the 2030s will be able to do rather well too, because it will see standard sirens to such great redshift, really beyond the redshifts at which we would see things like supernovae or be able to measure baryon acoustic oscillations. So that might even allow us to test more general cosmological models, models that involve things like extra dimensions or complicated departures from Einstein's theory that could be correct, that definitely need to be tested. So looking ahead to the 2030s, it's a pretty exciting landscape, not just in terms of electromagnetic observations of cosmology, but gravitational wave ones as well. And will that help us answer some of these big questions about the nature of dark matter and dark energy? Well, who can say? But we think it's going to be an exciting field to work in. And all I can say is, watch this space. So I hope the IT has performed okay and you've been able to follow all the slides and the connection has not dropped. I will now stop sharing my screen and I'll be delighted to answer any questions that you might have in our remaining time. Thank you very much.
Thank you, sir, for your wonderful presentation, sir. So we have got some question. So if you allow, we can start discussion session, sir. So the first question. So please explain the Hubble constant again and what is omega parameter.
Obviously, I did go rather fast, so let me be brief. Let me encourage you to watch the video again. You know, when I teach this to my students, they need to revise it and study it carefully over several times. But very briefly, the Hubble constant is measuring the current expansion rate of the universe, and the omega parameters are dimensionless numbers that tell us how much matter and how much dark energy there is. So if we can measure the Hubble constant and the omega parameters, that tells us not just what the universe is doing now, but what it was doing in the past, and even what it will do in the future.
Thank you, sir. And there is another question in the inbox. So what is the difference between hot and dark
matter and cold dark matter are two possible explanations for what dark matter is. What we know pretty much for sure is that the dark matter can't be made of atoms, because I briefly described this. I said that the computer simulations don't work correctly. They don't match the observed universe if the dark matter is made of atoms. Also, our predictions for the very early universe and the abundance of chemical elements, those don't check out correctly if the dark matter is made of atoms. And thirdly, actually, I didn't mention this, but the angular power spectrum of the cosmic background radiation, that doesn't check out either if the dark matter is made of atoms. So if it's not made of atoms, what is it made of? So two possible candidates would be, for example, neutrinos, but neutrinos move essentially at the speed of light. They do have mass, but not very much, so they travel very, very close to the speed of light. And that means they would be hot dark matter. And the reason that's a problem is that if you build your universe with all the dark matter in the form of neutrinos, then structure can't form because the neutrinos don't like being confined to clustered regions. They've got too much thermal energy and they can escape. So the reason that cold dark matter works better, just like I said in the talk, is that the dark matter doesn't have a lot of thermal energy. The particles are not moving fast. They're not moving at relativistic speeds. So they just sit there, attracting other matter towards them. And that helps the clustering to form, even though the universe is expanding. You can still have galaxies and clusters forming, even in an expanding universe. That's much harder to arrange if the dark matter is hot.
Thank you, sir. This may be the last question. So what will happen when the normal matter interact with the dark matter?
Well, to be honest, we don't know, because the dark matter seems to be very weakly interacting. It doesn't seem to interact with ordinary matter at all. It attracts ordinary matter gravitationally, but there doesn't seem to be any other interactions. But there are a few possibilities. Among the candidates for what the dark matter might be, could be some kind of exotic particle predicted in our theories of particle physics. And if such a particle did exist, let's say it was connected with one such theory, which is supersymmetry, then those supersymmetric dark matter particles, if they exist, might be able to interact with other supersymmetric particles. And that might reveal itself in different ways, not through astronomical observations, but through particle physics experiments. So all is not lost. We might hope to see dark matter interacting with ordinary matter, but it doesn't happen very often. So we have to look very, very hard to try to see it.
Thank you, sir, for your nice presentation and wonderful discussion, Chetan, sir. So
let me also say, if there are further questions, please do send them to me by email, and I'll be very happy to answer. I'm sorry my talk was a little longer than I expected.
So I think the
I'll be very happy to answer for further questions.
Yeah, sir. So the video will still remain in Facebook and the YouTube channel. So anybody can ask question later. So thanks again, sir, for accepting our invitation. So I think our students have learned a lot of things about the dark side of our universe, mainly the dark matter. So we know that about 95% of our universe are dark, so including dark matter and dark energy. So we have to know that thing. So and but you have started, and our next generation will maybe solve that problem. So, and thanks again for motivating our next generation by giving time, your valuable time, so to us. So I think some of our students may fall in love in dark matter research, and in near future they will find some solution. So thanks again. And the main aim of our program is to motivate and encourage our students in this corona pandemic situation. So we know that we are passing very tough time. This is the very new type of crisis in all over the world. So we are trying to adjust with this new normal situation, and online education is very important. So we have started from June 2020, and I'm very grateful to you and all other speakers who have helped me in doing this. And today I am completing 105th international webinar, and including 2 Nobel laureates in our 105th. So that is very great things, and I'm feeling proud, sir. So thanks again. If you have some suggestion for my student, for next generation researcher and student, you can say something.
Absolutely. So I will be happy to recommend some topics to explore. And I will send you some details by email about that, and please do pass them on to the students. The really exciting development of the coming years is that there will be a lot of data available to anyone in the world to use, because many of the upcoming instruments and satellites will be releasing their data very quickly for anyone to access. So you don't need a large telescope or a particle physics collider. You can still explore cosmology wherever you are in the world.
Thank you, sir. So thanks again, and I'd like to say thanks on the behalf of the Department of Physics, Pabna University of Science and Technology, for accepting our invitation, sir. We are celebrating our Victory Month, and yesterday we have celebrated our Victory Day, and so with the Nobel laureates, and Today, I'm completing our 105th International Physics webinar with you. So thanks again for helping me in arranging this important webinar with you. So
Thank
thanks
you. You're
again.
very
Bye.
welcome.
Yeah.
Bye
Bye
bye,
for today,
everyone.
and
Bye bye.
hopefully see you again.